Microwave hybrid couplers are elegant, purely passive four-port components that divide or combine electromagnetic power. By leveraging the foundational physics of wave superposition, they carefully manipulate phase delays so that signals constructively interfere at desired output ports and destructively interfere at isolated ports. The two most common types of hybrid couplers are the 90-degree quadrature hybrid and the 180-degree hybrid. Here is a detailed breakdown of how they work, from theory to physical realization. Theoretical background. In microwave network theory, a hybrid coupler is defined as a 3 dB directional coupler. This means it takes an input signal and splits its power equally between two output ports. Half the power is -3 dB, while preventing any power from flowing into a fourth isolated port. The operation of these networks is governed by three physical constraints. Reciprocity. The component is made of passive, linear materials, meaning signals can travel in either direction with the same characteristics. Lossless. In an ideal theoretical model, no power is lost to heat or radiation. Power in equals power out. Perfect matching. All four ports are matched to the system's characteristic impedance, typically 50 ohms, meaning no waves reflect back to the source. Microwave network theory dictates that it is mathematically impossible to have a lossless, reciprocal, and perfectly matched three-port network. You must have four ports to satisfy these conditions, which naturally results in one of the ports becoming perfectly isolated from the input.
The scattering S matrices. The S matrix maps how voltage waves incident on any port scatter to the other ports. 1. The 90-degree quadrature hybrid. If power is injected into port 1, it splits evenly between port 2 and port 3, but the wave arriving at port 3 is delayed by 90 degrees relative to port 2. Port 4 is isolated. The S matrix is written as shown below. Note, the J represents the 90-degree phase shift, and 1 over square root of 2 represents the half-power voltage split. 2. The 180-degree hybrid. Also known as the rat race coupler, this device has two distinct input behaviors. If you feed the sum port, sigma, the power splits evenly and in phase between the two outputs. If you feed the difference port, delta, the power splits evenly but 180 degrees out of phase. The S matrix is shown here.
Stripline realization. Stripline and microstrip technologies allow us to print these couplers directly onto a dielectric substrate using thin conductive traces. The branch line coupler, 90-degree hybrid. This is built as a square box of transmission lines. It consists of two parallel main lines and two parallel branch lines connecting them. Every side of the square is exactly a quarter wave long at the center operating frequency. To achieve the 3 dB split, the characteristic impedance of the transmission lines must be carefully calculated. If the system impedance is Z0, e.g. 50 ohms, the series main lines must have an impedance of Z0 divided by square root of 2, which requires wider copper traces, and the parallel branch lines must have an impedance of Z0.
The rat race coupler, 180-degree hybrid. This is built as a continuous ring of transmission line. The total circumference of the ring is 6 quarter wavelengths, or 1.5 wavelengths. The four ports are tapped into the ring. 3 of the spaces between the ports are exactly a quarter wave apart. The final gap between the first and last port is 3/4 wave long. The characteristic impedance of the entire ring trace must be square root of 2 times Z0, about 70.7 ohms in a 50 ohm system, which requires slightly narrower trace widths than the input ports. The different path lengths around the ring ensure that signals arriving at the isolated port are always exactly 180 degrees out of phase, canceling each other out perfectly.
Applications. Because of their phase relationships and isolation properties, hybrid couplers are indispensable in RF and microwave systems. Balanced amplifiers. By placing two identical amplifiers between two 90-degree hybrids, any reflections caused by a mismatch at the amplifier inputs are directed to an isolated port and absorbed by a resistor. This provides excellent voltage standing wave ratio, VSWR, and stability. Balanced mixers. 180-degree hybrids are used to combine a local oscillator, LO, and an RF signal into a mixer diode network. The 180-degree phase shift allows the circuit to cancel out LO noise and prevent the powerful LO signal from leaking back out the RF port. Antenna beamforming. Networks of quadrature hybrids and phase shifters, like the Butler matrix, are used to steer the beams of phased array antennas electronically with no moving parts. Power combining. They can safely combine the output power of multiple solid-state amplifiers into a single high-power transmission without the amplifiers interfering with one another. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.